Hello everyone, welcome to our new JS tutorial. In this tutorial, we are going to talk about AVL trees. Actually, I would like to make a videos for DFS, PFS, Huffman coding, other stuff, but due to time shortages, I have so many projects. I decided to make a video for now for AVL tree, and I will make just one video or organize offline, meaning just before finals. To revise everything. But anyway, if I have time, I will do also for other topics. But for now, let's focus on AVL trees, because AVL trees are much more difficult than, for example, Huffman encoding, because they have so many rules and rotations. So on this particular tutorial, I'm not going to analyze each particular case. What I'm going to do is just to show you how to rotate, or have to know how should you rotate. Okay, for example, whether you should rotate to the right or to the left. I'm going to teach you, I'm going to show you how to decide. Okay, so actually in this case, I just assume that but just basics of AVL tree. AVL tree is a tree where each node has some kind of balancing factor. Okay, so for example, let's say we have this tree. Okay, and we assume that this tree has a balancing factor, and as we assume, we have to find out the balancing factor. Okay, so let's say this is 2, and this is 4, and this is 5. And how do you find the balancing factor? Sorry for noise in the background. How do you find the balancing factor? You just find out just subtraction, just a result of subtraction of the number of the not the number, I'd say it's the height. Okay, number, I just want to say number of edges, but let's say the height. So you just subtract height. Okay, height in left sub 3 minus height in right sub 3. Doesn't matter, maybe you can find it just with minus of subtraction of the height in the right and then in the left, but it doesn't matter. Just first decide how you are subtracting. I'm going to subtract the left sub 3 minus right sub 3. Okay, so right sub 3. And what does it mean? The height, the height, for example, the height is a number of the nodes, from the root to the leaf node. For example, let's say this is left sub 3, and what's the height of this? The height of this is 2, because there are 2 nodes. Okay, for example, this A, height of A. This is not the height of height of A in the left sub 3. Okay, in the left sub 3 is what? Is 2. And assume that this A has also right sub 3, and this is like this. So what the height of the right sub 3 of A? This is 3, because we have 1, 2, and 3 elements. So height of A in right sub 3, okay, is what? Is, let's say, sub 3 is 3. So what does mean? The balancing factor of A is, and the height in the left, this is 2, and height in the right is 3, so minus, this is minus 1. So now you know how to find out the balancing factor. Okay, so in this case, what's the height of this 5? There's nothing in the left sub 3, so the height is 0. Okay, if there's nothing, so then it's 0. Okay, if nothing in sub 3, okay, sub 3, then height is 0. So the left and the right sub 3s do not exist for this 5. So the balancing factor in the left sub 3 is 0, so the right sub 3 is also 0. So overall, L minus R is 0. And the same goes for 2. And what about the balancing factor of this 4? So in the left, we have 1 element, so the height is 1. And the right, we have also 1 element, the height is 1. So 1 minus 1, the balancing factor is 0. Okay, so why I'm just showing you this. The point is that any tree is AVL tree. Okay, just remember it. AVL tree if the balancing factor, so theory, balancing factor of each node is in range. Is each node is in range of -1, 0, and 1. And what does it mean? The balancing factor of the nodes are either -1, 0, or 1. That means the tree is AVL. So in this case, 0 is in the range, so this is AVL tree. So actually, AVL trees are used in order to balance the tree, and that means, for example, if you want to insert the node, you have to, or just delete, you have to always be sure that you're always keeping the property of AVL. For example, when you insert some value here in this tree, you have to check once that the balancing factor of the nodes are in this particular range. So that means there's a question, when then should I rotate? So what does mean actual rotation? Rotation is changing the position of rotation is changing position of some nodes which have not satisfied balancing factor, not have, let's say, obtain, because see, actually in the very first case, before insertion or before deletion, our node, each node had, let's assume that the balancing tree in this particular range, -1, 0, and 1. But after insertion, some nodes now have the balancing factor, for example, 2, -2, 3. So then we apply rotation. So rotation is changing the position of some nodes which obtain, okay, not have, which obtain not satisfied balancing factor. That means not in the range after insertion, or deletion. Okay, so that means once you insert the delete node in AVL tree, you always have to be sure that the old nodes still have the satisfying balancing factor. So there are so many types of rules that you have to follow: right rotation, left rotation. I mean, the cases when you have to rotate to the right or to the left. And I'm not just going to just make this tutorial as a serial tutorial. This is a tutorial, so have to do some practical sessions. Okay, so let's say we have this tree. Okay, so I'm going to straight to the problem. Hope my drawing is okay. So 5, assume 30, 35, 32, and 40. So the very first thing to do is just to identify the balancing factor of each node. Okay, we are subtracting the height from the left subtree minus the right subtree. Okay, these are heights. Okay, let's say height of left subtree minus height of right subtree is balancing factor. Okay, this is BP, means balancing factor. So what's the height of the left subtree of 40? This is 0, and the right subtree is also 0 because there's nothing. Okay, so overall 0 minus 0 is 0. Let me delete it. So balancing factor of 40 is 0. So this is in range. 32 is also doesn't have any kind of subtree, so 0. And what about 35? 35 has one node in the left subtree. That means height is 1, and let's say 1, and minus what 1, because in the right subtree also there is one node, height is 1. So overall the subtree, I mean the height of the subtrees are 1, so overall balancing factor is 0 of 35. What about 5? 5 has 0 balancing factor because in the left and the right subtrees the height is 0 because there's no subtree. So what about 30? So actually in the left, we have one element. I mean, actually, the height is not the number of the nodes, okay? Just it's not always the case. The height is number of edges, okay? Actually, let's say height is the number of the nodes that you traverse till the leaf node, okay? Height is number of nodes from top, from root to the leaf, okay? Okay, so in this case, okay, it's 30, we go to the leaf, 32, we met this, okay, 35, 1, and we met this, 2, so we reached the leaf, so that's why we met 2. In our traverse, we made 2 nodes, so that's why our height is 2, it's not 3, okay? It's not number of the nodes, it's the number of the nodes, I mean, in general, it's the number of the nodes that you met while traversing from the root to the leaf node, okay? Just sorry for misunderstanding. Okay, so left subtree has 1, height, right subtree has 2, so 1 minus 2 is minus 1. So, okay, let's see. They have 0, 0, so all the balancing factors are in range. So that means what? This tree is balancing tree. So now let's consider the case when we insert 45. So if I insert 45, 45 comes here because, okay, because they have to follow BXT's rule. I mean, 45 is larger than 30, it goes to the right, it's larger than 35, it goes to the right, and it's also larger than 40, so it goes to the right. So after insertion, okay, let's say insert 45, and what I have is this. Okay, 35, 32, 30, no, 40, and I have now this 45. So let's quickly just rewrite the balancing factors, because balancing factors, of course, is changed. Okay, 45 has 0 balancing factor. 40 has what? 40 has minus 1. Why? Because the left sub. I mean, we are finding balancing factor from subtraction of the height in the left subtree minus to the right, because this is the case. I mean, this is a formula that we have to follow. Left subtree doesn't have any I mean, nodes, so this is 0, and this right subtree has 1, so 0 minus 1 is minus 1. So let me do it quickly. Okay, so 32 has 0 because nothing, and 35 has what? In the left, 1, and the right, 2. I mean, 2 passes to the leaf. Okay, so that means 1 minus 2 is minus 1. And what about 5? This is 0 because there's nothing. And what about this 30? In the left subtree, we have only one way in order to reach the leaf node. In the right subtree, we have to do what? We have to do 3 steps. Okay, I mean 1, 2, 3 in order to reach the leafless node. Okay, so that's why 1 minus 3 is minus 2. So 30 has the balancing factor of minus 2. And as you know, this is not in the range. Okay, we met the case when our node has not satisfying balancing factor. And in this case, we have to do what? We have to do rotation. But there's a question, where to rotate, to the left or to the right? So the answer is pretty simple, you know. So as you can see in this tree, where in which subtree we have more nodes. Sorry for the background noise, okay. So in which subtree we have more nodes. I mean, more elements. So but in the right subtree, right? Because in the right subtree we have too many elements. And so that's why when we subtract this height of the left and right subtree, we are getting minus 2. So that means in this case, we have to rotate to the left. Rotate to the left. But now we have identified that we have to rotate to the left, but which node we have to rotate? Which node should move to left subtree? Is it 32, 40? Which node we have to move to the left subtree? That's the question, right? So in this case, what do? We rotate, okay, not rotate, I mean, we rotate to the left, but we move through rotation the node that has not satisfying balancing factor. So in this case, which node doesn't have this balancing factor which is not in the range of -1, 0, and 1. So this is 30, right? 30, right? Because 30 has balancing factor of -2. So that means we have to rotate this 30 to the left, okay? Rotate to left, to the left, 30. Why? Why? Because it has none, I mean, not because it has non-satisfying negative, I mean, balancing factor. So this, okay, you understand it, so this balancing factor doesn't equal -1, 0, or 1, okay? So that's why we rotate this node. So firstly, you have to find out in which position to where you have to rotate. And then, I mean, in this case, to the left, because the right subtree has more nodes, too many nodes. And in the second case, you have to identify which node to rotate, which node to move to opposite subtree. In this case, you find it by checking the balancing factors. If balancing factor is not satisfying, you move it to corresponding subtree. So let's move then 30 to the left. When you move 30 to the left, okay, this 35 becomes the root, okay, and this 32 becomes the left, I mean, the right child of 30, okay? So let me redraw it again here, 35, 32, actually, I just forgot it, 30, this is 35, this is 32, okay? So this is 40 and this is 45. And when you rotate to the left, this is called, what how it's called? RR case, I guess, because we are rotating from the right subtree, okay? So this is called RR case, but just check it in presentation. My objective is just to show you how to rotate, okay? So when you move 30 to the left, okay, when you move 30 to the left, 35 becomes the head. And where do we put then this 32? Because the head has left subtree, but where do we put this 32? And this 32 becomes the right subtree of this, I mean, the right node or right subtree, okay? I mean, I cannot node, okay? Let's say left subtree, I mean, left subtree of the 635 that's going to become the head becomes the right subtree of the node that is moving to the left subtree. So generally we can assume, we can say like that. Let's say this is A and this is B and this is C. I mean, this is subtree, okay? There are not nodes, subtree, okay? Let's assume C is subtree, not the one node. There are, for example, many other nodes in this part, I mean, in the left subtree of this B, okay? This is 3, okay? So when you rotate to the left, this B becomes the head, and A becomes the left child of B, and this C3, this subtree moves to the right subtree of the A. Okay, we're going to see this case. In this case, is 30, this is 35, and this is 32. Okay, so okay, it's 30, 32, and just one subtree. Okay, I mean the one node in subtree. There may be other nodes. Okay, you may everything in this position. So this is 35. So let me do it. So this is 35. Okay, this becomes a head. In the left subtree, I have now this A. So this is 30. The right subtree of this 30 is becomes 32. I mean, this subtree, in this case, I have only one node in this subtree, so just 32. The left child of 30 is the same, this 5. And in the right side, what we have is that right subtree of 40. I mean, of 35 is 40, and also right child of 40 is 45. So this is the case. This is called our case where, I mean, we are rotating the node in the right subtree to the left. This is called RRK. So we check again in the presentation. So now let's calculate the balancing factor. This has 0 because nothing in the right and the left subtree. So this has -1 because in the left subtree there's no node. In the right subtree the height is just 1. So 0 minus 1 is -1, and this nodes have 0 balancing factor because there's no height, there's nothing in the left and right subtrees. So it has also 0 because the height of the left subtrees, the height in the left subtree is 0, and just 1 because there is one pass, one step in order to move to the left subtree, to the leaf of the left subtree, and to the leaf of the right subtree. There is also one pass. There's also 1, so 1 minus 1 is 0. So what about 35? The pass to the leaf node is just 2. Involves 2 nodes, just 1, 2. So the height of left subtree is 2. And what about the height of the right subtree? Is also 2, right? 1, 1, 2. So 2 minus 2 is 0. So as you can see, we now have the balancing factors. Satisfying balancing factors which are in the range of -1, 0, and 1. So we successfully transformed this tree, okay, to AVL tree. This is just tree. Okay, this is AVL tree. Okay, why? Firstly, this was this was AVL. This was AVL tree. We inserted the node, and then after insertion, after this, AVL is not AVL anymore. That means AVL is not satisfying its property. Balancing factors are not in range. Okay, so that's why we do rotation. Okay, this is the theory part. Okay, so we do rotation in order to again make AVL tree, which was initial AVL, again AVL after insertion. Okay, so we decide where to rotate. In this case, we rotate to the left. And why? Because we have more elements in the right subtree. Okay, so and then there is a question: which node to move, which node to rotate, and you find it by calculating balancing factors. You find you go from the bottom. You see, you compare balancing factors. They are all satisfying, and you reach here. 30 has non-satisfying balancing factor, so that means you move 30 to the left subtree. Okay, so now we move here. I've give you the formula or the structure that you have to follow. This general structure. Okay, same that A, B, C. C is what? C is left subtree. Okay, here might be, for example, after 32, for example, 29, and for example 33, and that means when I mean this subtree becomes right subtree of left subtree of B becomes the right subtree of A, that means all of these nodes move as a one subtree move to the here in this position. Okay, so that means if C was this, if C was 32, 29, and 33, after insertion, we should have got our B was 35, right? 35, then 30, and then what? 32 is C, okay? 29 and 33, because this is C, okay? This is C, this is A, and this is B, okay? This is B. So what I mean is that, for example, if there is 32, 29, 33, you move everything to the right subtree of this A, okay? Don't move just 32, okay? And if you move just 32, where do you place this 29, 33? You move everything, just each node in the subtree to the corresponding position. This is the case. So this is a formula in case of right rotation. Okay. So as I see, the videos just went pretty long, and in this case, in this particular time, I'm going to finish this video, and I just think that I have to make several videos for each case. Now we analyze how to rotate to the right, okay, see how to rotate to the left, actually, how to rotate to the left. Okay, this is not right, so right rotation, this is left rotation, right. I mean, I just want to say that, I mean, a left rotation from right subtree, okay? A left rotation from right subtree. So anyway, this is in this particular case, we analyze that what is AVL tree. I have to just find balancing factors and have to rotate to the left. In the next videos, I'm going to try to make as videos. Hopefully there will be before a final, at least. So I'm going to analyze, have to rotate to the right, and have to delete, and then just transform the AVL tree. Because when you, as you see, when you insert your AVL tree, it's not always just AVL tree. It's not, it doesn't always maintain its property, okay? For example, balancing factors may change as here. It became -2. So that's why you have to do some rotations to convert it again to AVL tree. So that's why you have to know how to do it, some cases, some formulas. So now this is a formula in order to, this is how you rotate to the left. So again, in other videos, in the next videos, we're going to analyze how to rotate to right while insertion, and also we'll analyze 6 cases of deletion. So again, see you soon in our next JS tutorial, and I hope it was helpful for you. Just don't forget to share it with your friends, and please just ask questions so that I can see you are watching and you are trying to understand, because our goal is to help people.